Hello everyone, welcome to this next video on classical mechanics. In the previous video we saw the derivation for Hamilton's canonical equations of motion, and in this video we shall see an example for solving or calculating the equations of motion when the case is of simple pendulum. This case we also discussed when we derived the equations of motion using the Lagrange equation. Now let us see what is the Hamiltonian corresponding to this, and making use of this Hamilton's canonical equations of motion, how can we reach at obtaining the equations of motion. So here this is the simple pendulum that is being attached to this string of length L. This point is A, this point is C, this point is B, and it is hanging from the point O. The length is L and the angle here of oscillation is theta. We have assumed mass of the bob is m, length of the string is L, and theta is the angle between the rest position and the deflected position. These are the assumptions. Moreover, the generalized coordinates here are to be taken as r and theta, as we discussed in the previous videos, right? The constraint that is applied over here is that the length of the string is fixed. So our r is fixed. We are only left with one generalized coordinate, that is theta. So here q1 is only theta. So that is the generalized coordinate. So first of all we will calculate the kinetic energy as we done previously. This kinetic energy T is calculated using the formula half mv square. V square is basically the time derivative of displacement or the distance s. Now what is the distance s over here? So this is the distance that this bob covers from the point traveling from point A to the point B. So how can we calculate that? By making use of this formula, arc length by radius is equal to the angle suspended by it. So from here s comes out to be L theta. So it's the derivative of s would simply be L into theta dot. Why? Because L is constant. So and our generalized coordinate, that is theta. So we have substituted the value over here, and this comes out to be the kinetic energy. So next thing is to calculate the potential energy. Potential energy is usually calculated by this formula mgh, where this height is taken from some reference level. So here we take the reference level to be point A. That means we'll say this initial position is our reference level. So when we are at B, we have moved up from this point A this much distance. So we need to calculate what this distance is, that is this much height, right? So it would be the total length minus the length OC. So the total length OA minus the length OC, and we can calculate this length using trigonometry, right? Using this angle theta. So we can arrive at this expression of 1 minus cos theta. Why? Because the whole length is L. This length, this much portion, this is L cos theta, by virtue of this angle theta and this angle being 90 degree, right? So the length CA, that is h, that would be L minus L cos theta. So it would simply be mg L minus L cos theta. So it would be this one. So the Lagrangian is given by T minus V. We have T with us, we have V with us, we just substituted the value. So in previously we used the Lagrange equation, that was del L by del theta minus ddt of del L by del theta dot is equal to 0. So this we had used in the last video, and we have seen what are the equations of motion using this. In this video we'll make use the Hamiltonian. So we know by definition this Hamiltonian is given to be summation pj qj minus L. So that means whatever number of generalized coordinates we have, that many terms do appear here. But in our case we only have q1, which is equal to theta. So we only have the term this momentum corresponding to the variable theta, and the generalized coordinate theta, and its derivative qj dot minus L is this thing, so we have just substituted this quantity. So now proceeding further, because we are in Hamiltonian and we know for this this Lagrange has basis. Now because we are dealing with theta, so it would be our generalized coordinate is theta, so that means it would be theta dot and t, and now we are shifting to Hamiltonian approach, so it would contain the generalized coordinate, that means theta, and the momentum corresponding to this coordinate, let us call it by p, and with the subscript theta suggesting it is with respect to this coordinate theta and time. So here we are to eliminate this theta dot from our Lagrange, from this expression h. So wherever this theta dot is appearing, we have to get rid of this. So for doing that, what we can do, we can just calculate theta dot using the expression this. We know Pj is equal to del L by del Qj dot. This is the very important relation. One must remember this one. We have L with us. This is our L. So we have to differentiate it with respect to Qj dot. Qj here is theta, so it would be theta dot. So when you take the partial derivative of this L with respect to theta dot, you will only get half m L square as such, because these are constants, into 2 into theta dot. So basically we are left only with this term. So that means you got a relation between p theta and theta dot. So you can, as for now, you can substitute the value of theta dot in terms of p theta. So we have just replaced this thing. We have just replaced theta dot here and here using this expression. So we are left with p theta as such, the value of theta dot from here, minus half ml square as such, and the value of theta dot square from here, right, and this term as such. So when you simplify this a little, you will be left with h is equal to this thing. So now once we have h, now we can use Hamilton's canonical equations of motion. And what are they? You also have to remember these, right? So these were qj dot is equal to del h by del pj, and pj dot is equal to minus del h by del qj, right? So these are the canonical equations that we were looking for. And in our case, because our q1 is theta, so that means we have qj as theta dot and pj as p theta dot. So similarly, we have just replaced these notations, right? And we can calculate the values of this and this from the given Hamiltonian here. So we can partially differentiate this h once with respect to p theta, another time with respect to theta. So when you differentiate this quantity with respect to p theta, from first term you will be getting half into 2p theta. Half by ml square would be constant, so you just have to differentiate p theta square, so it would be 2 into p theta. 2 and 2 cancel, so we are left with this term. Similarly, when you differentiate this h with respect to theta, the first term would give you 0 because we are doing it partially, and from the second term this term would again give you 0, and ml multiplied by this cos theta would give you mgl sine theta. The derivative of minus cos theta would be sine theta. So you can substitute these values into these equations. So what do we get? We get theta dot is equal to, here in place of del h by del p theta, we just have to write this term, and similarly here we write this term, right? So these are the equations of motion when we are in when we are using the Hamiltonian's approach. But to match this with the ones with the equations of motion that we obtained previously, what we have to do, we have to again convert our basis from now, because now we are in Hamiltonian approach, so our basis is qj pj t. So we have to go back to this basis to see our equations of motions. So in doing so, we have to eliminate this pj. So what we can do, we have calculated the value of this pj, right? Pj basically is p theta in our case, because our generalized coordinate is theta. So that means p theta is equal to ml theta dot, ml square theta dot. So we can just substitute it into our given equations, right? So when you substitute it in the first equation, you will get theta dot is equal to theta dot, so which is meaningless to calculate, right? And when you substitute it here, you add p theta as ml square theta dot. So when you calculate the derivative of this thing, you'll be getting p theta dot, that would be ml square, because these are constants, they'll be left as such, and you just have to perform the time derivative of this theta, so you'll be getting double dot. So replacing this value over here, we'll get this, and the right hand side would be the same. So you see m cancels with m, l square cancels with l, we are left with l theta double dot plus g sine theta is equal to 0, and when our angle of deflection is small, in that case we say the sine of theta that is nearly equal to theta, so we just replace this sine theta by theta. So this is our second order differential equation, which represents the motion equation of motion for the simple pendulum, and this is exactly the same equation that we have derived using the Lagrangian approach. So now you must be thinking, when we have other notions also to describe this kind of equation, why do we use such methods? And because very easily we can derive these equations from Newton's law, and also we have seen that we can derive this from the Lagrangian's approach. So why do we need Hamilton's canonical equations or the Hamiltonian approach to calculate such equations? You'll see the answer to this question in the next video, where I shall be talking about the application and the advantages of using this Hamiltonian approach. Well, that is it for this video. In the next video, we'll see the answer to this one, why we are learning this lengthier approach to solve such simple problems. So that is it for this video. Thank you for watching.